Welcome to the most comprehensive data preprocessing masterclass you will find anywhere. Here is a secret that every experienced data scientist knows. When you work on real-world projects, actually building the machine learning model is the easy part. It's the smallest part of the job. Studies consistently show that data scientists spend 80% of their time just on data preparation, cleaning, transforming, and organizing data. The model is just the final 20%. So if you consider preprocessing, you master 80% of data science. According to recent industry research, over 50% of errors in machine learning stem from inaccurate or incomplete data sets. And 40% of data scientists report spending more than 80% of their time cleaning and organizing data. This is not just a chore, it's a foundation of everything we do. There is an old saying in computer science, garbage in, garbage out. This is nowhere more true than in machine learning. If you feed a model poor quality data, it doesn't matter how sophisticated your algorithm is. The results will be poor. A simple model on clean data almost always outperforms a complex model on messy data. Research indicates that improper handling of missing values alone can lead to an 80% drop in predictive accuracy. Preprocessing is not just a chore to check off. It's a foundation of everything that follows. Data preprocessing enhances input data quality and the accuracy of results, ensuring that models run on datasets with completeness, systematic structure, and absence of distortion. By the end of these 5 hours, you won't just understand preprocessing theoretically. You will know exactly how to handle messy Excel exports, corrupted CSV files, inconsistent date formats, and text data that needs to be cleaned, and datasets with billions of rows. You will have a complete toolkit you can apply immediately to your own projects. We will cover everything from basic cleaning to advanced techniques for denoising data, which smooths data while preserving underlying structure. Let's begin. Before we dive into the data itself, let's talk about our tools. While there are many options out there, Python has become the undisputed king of data science. Why? Because its incredible ecosystem of libraries specifically built for data manipulation. We will be focusing on 3 main libraries throughout this tutorial: Pandas, NumPy, Scikit-learn. These libraries have become the industry standard with millions of downloads and active development communities. According to recent surveys, over 70% of data scientists use Python as their primary language, and the vast majority rely on these core libraries for preprocessing tasks. Pandas is our workforce. It gives us the data frame, a powerful table-like structure that makes manipulating rows and columns intuitive and fast. NumPy works underneath Pandas, providing fast numerical operations on arrays, and Scikit-learn provides us with preprocessing tools like scalars, encoders, and transformers that integrate seamlessly with machine learning pipelines. If you are following along, you will want to have Jupyter Notebook open. It's a perfect environment for preprocessing because it allows us to run code in chunks, visualize our data, and see immediate results. We will also be using pip install pandas, NumPy, Scikit-learn, Matplotlib, Seaborn to make sure we have everything we need. For those working with very large datasets, I will also mention Dask libraries that extend pandas to handle out-of-the-core computations on datasets that don't fit in the memory. The most common format you will encounter is the CSV, comma separated values. It is simple, lightweight, and almost every system can export to it. In Pandas, reading a CSV is as simple as df equal pd.read_csv of filename.csv. But watch out, there are pitfalls. Sometimes the separator is not a comma, it might be a semicolon or a tab. That's why read underscore CSV as a sub parameter. We also have to watch for header rows encoding issues. A common error message you might see is expecting XX lines in SA YY. This often indicates an erroneous CSV file or wrong encoding. Always specify encoding equal to UTF-8 or encoding equal to Latin-1 to avoid character decoding errors. In the corporate world, data lives in Excel. Pandas handles this with pd.read_Excel. But Excel files are notoriously messy. They might have multiple sheets, merged cells, formulas, or formatting that confuses the parser. We need to specify the sheet name, sometimes skip rows, and always check that the data was read correctly. Excel files are where pre-processing challenges are born. You might encounter dates stored as strings, numbers stored with $signs, or columns with mixed types. The dtype parameter lets you specify types for specific columns to avoid surprises. Remember that Excel files can also contain macros, hidden rows, and conditional formatting that don't translate well to data frames. For larger projects, data comes from SQL databases or APIs. With pd.read_SQL, we can connect directly to databases like PostgreSQL or MySQL and write SQL queries to pull exactly the data we need. For APIs, we use the request library to fetch JSON data, then normalize it into a data frame using pd.json_normalize. Each source has its own quirks, but Pandas provides the tools to handle them all. For truly massive datasets, millions of billions of rows, we might use Dask.data frame, which mimics the Pandas API but operates in parallel and out of the core. The air quality and bike sharing datasets, for example, are commonly used for testing pre-processing techniques on time series data with millions of rows. When you first load a dataset, you are essentially blind. You have thousands or millions of rows but no idea what they look like. The very first command I type always is df.head. This shows me the first 5 rows of my dataset. It's like turning on the lights in a dark room. I can see the column names, get a sense of what kind of data each column holds, and spot obvious issues immediately. Is a column supposed to be numbers but I see text? That's a red flag. Is there a column of IDs that I should drop later? I will see it here. Sometimes I also use df.tail to check the last 5 rows of the dataset. Sometimes the end of the file has different patterns or even footer information that should not be there. Next one is df.info method. This command gives you a concise summary of your entire data frame. It tells you how many rows you have, how many columns, and most importantly, the data type of each column and how many non-null values exist. This is where you discover your first pre-processing challenges. You might see columns that should be integers but are stored as objects. You might spot columns with missing values because the non-null count is less than the total rows. You also get a quick estimate of memory usage, critical when you are working with large data sets that might push your computer's limits. In one glance, .info tells you what needs fixing. For numerical columns, .describe is pure gold. It generates the main descriptive statistics like count, mean, standard deviation, minimum, quartiles, and maximum. This gives you a mathematical fingerprint of your data. A mean that is very different from the median suggests skewness. A standard deviation that is huge related to the mean suggests high variability. A minimum or maximum that seems unrealistic, like negative edges or temperatures in the thousands, immediately flags outliers. For categorical data, you can use df.describe with parameter include equal to object to get familiar information like count, unique values count, top category and frequency of the top category. This statistical snapshot guides your entire preprocessing strategy. Finally, a simple but essential attribute, that is dot shape. It returns a tuple with number of rows, number of columns. This tells you the dimensionality of your data set. Are you working with 1000 rows or 1 million rows? With 10 features or 1000 features. Your answer dictates everything. What techniques are computationally feasible, whether you need to worry about memory optimization, and even which algorithms you can realistically use. Check dot shape early and check it often throughout your preprocessing to ensure your operations have not accidentally dropped rows or added unintended columns.